Thanks very much. I'm really delighted to be here. Before we start, I would like to thank Mr. Turkman, Yaman, and Gun Bilgin for inviting me and for their hospitality. I really believe that if in any country we had as passionate people as they are, in any country, we can sort out the treatment for any disease in the world. Now, before I start, if there is anything that I say and is not clear, you can do two things. First, blame the translator, and then you can raise your hand and ask me. Now, as you see, does this work? Or? Okay. I work at Stanford Department of Psychiatry and Behavioral Sciences, and our work is focused on understanding the molecular mechanism of Down syndrome. Now, Down syndrome has been described centuries ago as you see, this is a painting that found in Belgium showing that, you see, even as faces of angels shows the special facial features of people with Down syndrome. Now, as you were aware, Down syndrome is a multi-system disorder, meaning that it's not just cognitive dysfunction. It also affects the cardiovascular system. It affects the digestive system. It affects the skin system. And then the idea is that during the last maybe few decades, most of these aspects, except the cognitive dysfunction, has been significantly improved, meaning that by significant improvement in surgical method, a lot of problems that they had in terms of cardiovascular problem has been taken care of. Because of that, people with Down syndrome used to live maybe a few decades ago only 2-3 years, and now they go beyond 60. But the thing that has not been really tried to understand and find a treatment has been the cognitive dysfunction. What are the molecular mechanisms of cognitive dysfunction, and is there any way to improve it, or not even improve it, but at least slow down the process of regression? By doing that, at least you can significantly improve their life. And I have to clarify that we are not trying to change the personality of individuals with Down syndrome. We are not trying to change the shape of their faces. The only thing that we are very concerned is that to improve their cognitive function, make them do better at school. Now, the idea that we are working is that, okay, as Yaman mentioned, Down syndrome is caused by one extra copy of chromosome 21. And fortunately, chromosome 21 was the first chromosome that was ever entirely sequenced. Because of that, we know that there are 300 genes sitting on this chromosome. And the idea that we have is that each gene, overexpression of each particular gene, is able to cause one of the symptoms, meaning that, let's say, gene A and B cause cognitive dysfunction, and then the other genes cause cardiovascular problems, and the other ones called GI problems. Meaning that this idea is called one phenotype, one genotype, or from genotype, phenotype, meaning that you relate things that happens in terms of cognitive dysfunction, things that happen in cardiovascular problem, you can relate that to individual genes. By doing that, we can dissect the disease into different portions and only target the important genes that overexpression of those particular genes causes cognitive dysfunction. Now, this is a simplified method, is that, look, we have extra chromosome 21. There are 300 genes sitting there. Either directly or indirectly, they cause individual signs and symptoms of Down syndrome. And that's the idea that, again, I mentioned that one gene, one phenotype. Now, let's make it very simple. This showed a very simplified method, saying that, look, every one of us has 2 copies of a gene, but an individual with Down syndrome has an extra copy, and that we call that red. I think is The red copy is an extra copy. And then overexpression of these individual genes causes dysfunction of brain networks. When there is a dysfunction of this brain network, that leads to cognitive dysfunction, very simplified. But by looking at this shape, you can think that, okay, how are we going to treat this disorder? Okay, one simple way is that let's get rid of this extra copy. The other one would be, looking at the networks that undergo dysfunction and fix their function. They're either we take the genes out, or we say, oh, maybe it's too late, maybe this has happened. Now we go the networks that are affected and try to fix the function of those networks. Let's start for the first one. How do we identify the genes? Because we have 300 genes. We have to go one by one and identify these genes. The way to analyze that is to make a mouse model. And by making a mouse model, you have, as I say, chromosome 21 in human, but most of the genes in human are similar to genes in mouse chromosome 16, not 21. Then all the genes, or most of the genes that are sitting in chromosome 21 in human are found in mouse chromosome 16. That's why in order to make a mouse that let's say, a Down syndrome model, you make a mouse that has, instead of 21, has 3 copies of chromosome 16, right? And then what you're saying that, okay, let's make a mouse that has the entire piece. Let's make a mouse that has a shorter piece. Let's make a mouse that has only this piece and this piece. By doing this, when you compare them, you say, okay, which one of these mice do not do well in memory? By doing this, when you compare that, you see, okay, for instance, if this mouse, for instance, here, does very well, and this one doesn't, then probably the gene that is sitting here is the one that is important. Then you compare that, then you make a mouse model that has only these part three copy, it's in 3 copy expressed. And then most probably, this mouse also shows cognitive dysfunction. By doing this, you kind of dissect it, playing around with these genes and identify which portion was important. When you identify the portion, you go and have a list of the genes, and then you take those genes one by one out. One of the genes that is shown here is called APP, amyloid precursor protein. Now, in order to go further, I have to build a context that why this gene is important. This gene, amyloid precursor protein, is a major player also in Alzheimer's disease. As you may know, every individual with Down syndrome after the age of 40 years will show pathology which is absolutely similar to Alzheimer's disease. And then when they get older, most of them show clinical dementia of Alzheimer's type. Then this is the first link. Then every individual with Down syndrome will have a brain which is very similar to Alzheimer's disease, and then eventually develop Alzheimer's disease pathology and clinical aspects. The second link is that this gene, as I said, APP, if you make a mutation in APP, make a little bit of different form of APP, always leads to familial forms of Alzheimer's disease, meaning that indeed this gene APP is a major player both in Alzheimer's disease and Down syndrome. Now, you can ask a question, if really you're right, if really APP is that important, what happens if you take this gene out? And that has happened by nature. There are individuals that instead of having entire chromosome 21 triplicated, they have a fragment of chromosome 21 triplicated. These are called segmental trisomy. Now I tell you a story. The story is that there's a lady, she has Down syndrome, then she becomes very old. She does not show the signs and symptoms of Alzheimer's disease. Her brain does not shrink. She dies, they look at her brain, it's very normal. And no plaques, no tangles, no Alzheimer's. And then that's a puzzle. What's going on? When you look at the sequence of her chromosome 21, you see that the APP was missing, meaning that because she didn't have the 3 copies of APP, she never developed these signs and symptoms of Alzheimer's disease. That's why I'm trying to make a good link between APP and the symptoms. I think by now you're convinced that if we want to put all our money on one gene, let's start with APP. Then now we go. Now, the strategy that we use is that, OK, there are already drugs developed. These drugs are able to significantly reduce the expression of APP. Don't forget, we are not trying to knock it out. We are not trying to completely shut it down, because we need it for our normal function. The only thing that we need to bring it from a little bit more to the normal level. We are not going to completely get rid of it. Because of that, we are using these drugs. And then our idea is that what happens if during the early childhood, only that particular gene from 3 copies becomes 2 copies? And then let the kid grow, let the kid grow all these neurons and all these connections. And then if you let it go back to trisomy, what happens? The idea is that the trisomy, or having 3 copies of 21, or especially APP, is only important for the few years at the earliest stage. If we can, by using this drug, reduce that, we can significantly improve cognitive function in people with Down syndrome. Now, as I said, we are testing right now using a special drug that we are using. We have been able to significantly reduce the expression of APP in our mice. And right now, we are testing whether these mice would do better in cognitive function. OK? Now, we go to the next strategy, which I said is looking at circuits. Let's say, OK, we are identified one gene. I'm sure it's not only one gene. There are many, many more genes. But I guess this is a major player. But this was the first strategy. Let's take this copy and reduce that. The second strategy was that, OK, we know because of overexpression of this gene, there are some networks affected. Let's see what are the networks affected and then fix those, right? And then now your question is that, OK, what are the networks? One area in the brain that significantly shrinks, becomes smaller, and shows degeneration is called hippocampus. Hippocampus is a major player in learning and memory, and a special type of memory called contextual learning. Contextual learning is a type of memory that you put combination of a lot of cues and spatial memory, and all together build some kind of memory that by putting all these signs and symptoms, you can identify the location of individual objects. As you see, as I mentioned, hippocampus, if you want to use an analogy, is like a processor of a computer. What it does, it processes the data and then sends it for later storage to other places. Then is this network important? Yes. Why? Because there's a significant shrinkage. There's a significant degeneration of hippocampus in people with Down syndrome. Now, when you look at these neurons, you see that there is when you look at these neurons, there is a place in the brain called dentate gyrus. This is a mouse. Think about that, how human brain in probably 1,000 times bigger than a mouse brain. But I mean, if you look at this, in mouse, there are 1 million of these cells. And each cell is able to make another 5,000 connections, meaning that you have something like, if you have both sides, you have 10 billion connections just in a mouse's brain. By doing such a complicated connections, it allows the mouse, and eventually human, to build some kind of contextual learning. Now, when you look at these neurons, these are all the connections, because these are the dendrites, and through these dendrites, neurons are able to communicate with each other. As you see, this is a normal mouse, because you call that 2 normal chromosomes, and this is a trisomic mouse, because it has an extra chromosome 16, which is similar to 21. You see, the mouse that is affected here has significantly shorter connection, meaning that these neurons are indeed affected. Now, as I said, hippocampus works like a processor. It receives the information from different sources, processes them, builds some kind of map, and sends this map for storage in a place. Like any processor, the function of the processor, it depends on a lot of modulators. And these are the modulators we can name. You see, there are several of these modulators that what they do, they regulate the function of the hippocampus. Now, very interestingly, all these regions undergo significant atrophy and shrinkage in people with Down syndrome and Alzheimer's disease. This is one. The other one is that if you go in mouse and deliberately lesion them, destroy them, that causes significant cognitive dysfunction, meaning that indeed these are not doing the memory, but regulate the amount of memory here, meaning that these regions indeed play a significant role in building memory, learning and memory in people, right? And now, let's go to one of them, because we don't have time to go through all of them, but we have studied all these modulators one by one. There is a brain region that this brain region is called locus coeruleus. The reason that they call it locus coeruleus is blue, and it's a blue dot. And then these neurons send major connections to the entire brain. Apparently, there are, for instance, in mouse, there are only 5,000 probably 5,000 altogether. In rat, but in mouse, there are 2,000. And then sends to billions of cells in the whole brain. That's why one cell is able to modulate the function of thousands of other cells. That's why it's such an important, anything that goes wrong with these cells, there will be a significant problem with cognitive function. Now, as I said, this is a locus, and then what it does, it sends everywhere. All these neurons throughout the brain receive some kind of connection from these 2,000 cells. That's why, again, I'm just stressing the fact that these 2,000 cells, although there are very few, because they're very few, play a major role in cognitive dysfunction. Anything that happens to these 2,000, the entire brain would suffer because they lack the modulatory influence that they are supposed to put on the rest of the brain. Now, these are, you see, this is the way that you stain them. You label these neurons, and what we did, we looked at these locus cells, and then we found that indeed this area undergoes significant degeneration or atrophy in our mouse, meaning that our mice have a significant loss of these cells as a model for Down syndrome. Now, it's okay, we can. Now, what we did here is that let's look at our mouse, this is a mouse that we are looking. It's called TS65DN. Is overexpresses around 130 genes. And then we wanted to see what happens in our mouse model. What we did, this is a locus coeruleus, as I mentioned. And you see, this is a normal mouse. And this is a mouse model of Down syndrome. You see, there is a significant loss of these areas. Here, you don't see these cells here, meaning that there is a significant loss of these cells in mouse models of Down syndrome. Now, if you see whether, okay, if indeed really this happens, is there any signs and symptoms happening in cortex and hippocampus, we measure that indeed because of lack of release of norepinephrine in locus coeruleus, there is a significant shrinkage of these cells. What is the role of locus coeruleus? These cells are the sole provider of norepinephrine. They send projections to the brain, they send projections to the hippocampus, and what they do, they release norepinephrine. Now you're thinking, you say, okay, if this area going down, and if this area makes norepinephrine, it's very obvious to think that let's add some norepinephrine in these mice, right? If I add some norepinephrine, I inject some norepinephrine to these mice, I should be able to fix the problem, right? And then I'll show you this back. But now, there is a problem. The problem is that norepinephrine does not get into the brain. There's a barrier that this barrier protects our brain from all the drugs and medicine that we get. That's why not everything that you take should be able to cross and go to the brain. Because of that, there is this barrier that most drugs are not able to cross. But that's why we have a problem here, because norepinephrine cannot go there. Now we say, okay, in order to fix that, let's find another drug that is able to break down into norepinephrine. This is a drug, we call that LDOPS. This drug very easily crosses this barrier, and goes to the brain. But there is another problem. Another problem is that there are a lot of receptors for norepinephrine in the periphery. It's on our heart, is on our blood vessels. If you use norepinephrine, you're going to significantly increase the heart rate. You're going to significantly increase the blood pressure. This is released when the animal is in danger. When he's in danger, he doesn't need to send the blood to the brain. He has to send it to the muscles, increase the heart rate, and just run. But now the problem is that if we give these, in our mice, this prodrug, that's great. That can be converted into norepinephrine, but it's going to significantly increase the blood pressure and heart rate. That's why we cannot do that. Now, in order to fix that, we used something that inhibits the conversion of our drug to norepinephrine. And this inhibitor cannot cross this barrier. What does this mean? Meaning that the conversion of our drug to norepinephrine happens only in the brain, not outside the brain. Is that clear? Now the question is, what are the methods that we use? Okay, we have a mouse model. We know that this mouse shows the generation of locus coeruleus. How do you measure memory in mice? And there are several ways. One way, to put a poor mouse into this cage and shock him. And when you give him, if the mouse sits in this context, and then you shock him, he's never going to forget that. Every time that you put a mouse back into that room, he's going to freeze because he thinks that, oh my God, these crazy scientists are going to shock me again. Now, because of that, it's not going to work. And this is an indicator of memory, because if I don't remember, I won't freeze. This is a meaning that you use this, you put a mouse here, you shock him, then take the mouse back. Tomorrow, you put a mouse there. A normal mouse would remember, would freeze. But a mouse that has trouble with memory is not going to freeze. And then that's the indicator of memory. This is one way. This is called contextual learning. The other way is that mice by nature are very interested into novelty, the things that are new. That's why if you put two toys here, one that is old, one that is new, if by a camera you watch that, you see that you can see how much of the time the mouse spends with a new object versus the old object. If the mouse is normal, he knows what is old, what is new. But the mouse that has trouble with memory, to that mouse, everything is new, right? That's why by doing these two tests, you quantify memory in mice, right? Now, this is what we did. Okay, we know how to measure it. We put a mouse into this cage. We shock them. We put them again and measure how much does it go. We know what drug to use. It's called LDOPs. That drug breaks down into norepinephrine. Let's do that. You see, the mice that are not getting any treatment, there is a significant difference between our mouse, I mean the trisomic mouse, and the Down syndrome mouse and normal mouse. But the mouse that got treatment a few hours before, you see there is no difference. Meaning that by giving this treatment, we were able to restore contextual learning in our mice. Now, one of the other tests, very simple test, is a process called nesting. Mice by nature are able to make nestlets. You give them a little bit nestlets, and what they do, they make these nice and fluffy houses, and then sit in it, right? And you see, this is a normal mouse. You give them a little bit of this. After a few hours, you see, and they make a nest. But then the Down syndrome mice, they don't touch it, or if they touch it, they do it a little bit of the job. What does it show? One idea is that it's a matter of attention, because a normal mouse pays attention to this. That's why he's able to take care of these nestlets within a short period. A Down syndrome mouse doesn't pay attention. Because it doesn't pay attention, it takes him much longer to build that. If you put that for a long time, both mice make that. It's going to take, if you, instead of 2 hours, wait for 24 hours, they will make it. But within a short period, these mice do much faster than this. And this is an indication of attention. And as you know, around 40% of people with Down syndrome show ADHD, which is a problem with attention disorder, right? And that's why what we are thinking is that our drug would significantly improve attention, and when you pay more attention, you learn better. And now this is a mouse. This is a normal mouse, doesn't change. This here you measure how much nesting, how much house he builds, right? Normal mouse doesn't matter or doesn't care whether we give him a treatment or not. But this mouse is a Down syndrome mouse, right? Normally, he doesn't use his nesting. He doesn't use his house. We treat him, he uses his house. When we let him without the drug, he goes back to where it was, meaning that the drug was able to significantly improve nesting and attention in mouse models of Down syndrome, right? Now, again, go back to idea that, wait, you said norepinephrine has a lot of side effects. What happens if you give it to your mice? Because of that, we are measuring it here. This is an infrared detector. You put it on the mouse's neck, and what it does, it live quantifies the heart rate, the blood oxygenation, respiratory rate. These tests wants to make sure that whether they do fine in terms of cognition. And as you see, the mouse sitting there normally, and this has this infrared, and thanks God cannot cut that. But then within a few hours, you see that our drug does not cause a significant side effects, meaning that the mouse did not suffer from hyperactive, too much heartbeat, or increased blood pressure, or respiratory, or didn't change his blood oxygenation. By doing this, we are taking care of, yes, we are aware of the side effects. Does that mean that I have to stop or no? Okay. Now, okay, let's summarize. The summary is that we found an area that is called phenotype that significantly undergoes degeneration, and this is a phenotype. This area called locus coeruleus, and you were able to fix it by giving a drug that is able to convert into norepinephrine. But why? What gene did it cause that? Because the whole idea was that identify that gene, right? I think if I ask you now, what gene should we look? You're saying that, oh, let's start with APP. Now we go back to that gene and say, okay, this is a normal mouse, doesn't show much problem in his locus. This is our Down syndrome mouse. There is a significant shrinkage in this mouse. This is also a Down syndrome mouse, but we took that extra copy of APP out. By taking that extra copy of APP out, you significantly improve the status of locus coeruleus in these mice. What does that mean? Mean that, yes, locus undergoes significant degeneration, and one gene that could be the cause is APP, right? This is one link, that too much of APP, because every person with Down syndrome, most of them have too much APP. Too much of that caused loss of these cells. Loss of these cells caused low norepinephrine. Low norepinephrine caused failure in memory, right? Now you can do two things. Either bring down APP, don't let them cause degeneration, or give them norepinephrine. But now there are new sets of data coming out during the last few years, is that the story is actually a little bit more interesting than we thought, is that if you make a mouse model, as you remember, I said, every individual with Down syndrome will show a brain very similar to Alzheimer's disease. Okay, now your question is that if you make a mouse model for Alzheimer's disease that has a lot of those pathology in his brain, what happens if you destroy that area that you're interested, locus? Apparently, when you destroy that, you significantly increase pathology. What does that mean? Mean that locus plays a significant role, is increasing when it goes down, significant increase in pathology. Think about that. People with Down syndrome convert into Alzheimer's disease. Apparently, when the locus coeruleus undergoes degeneration, that speeds up the process. Then what does that mean? Mean that we could use norepinephrine to not only improve cognition in children with Down syndrome, but eventually we can prevent their conversion when they become adult to Alzheimer's disease, right? Now, this is that you see the down. That's why, interestingly, improving norepinephrine signaling, it has a dual effect. One, improving the cognition. Two, is helping us not to these individuals convert into Alzheimer's disease, right? Now, so far, I mean, the conclusion is that we know that there is a brain region called locus coeruleus, makes norepinephrine. If you increase norepinephrine, improves cognition. APP is a major player. If you cause degeneration of locus, you're going to increase pathology. You make them become Alzheimer's faster. If you increase norepinephrine, you're going to delay the speed that they become Alzheimer's disease. And now these are the members of my lab working. What I have to stress to you guys is that the majority of the funding from my lab is coming from parents like you. And these are parents that not necessarily very rich, but they realize that they cannot wait for someone else, meaning that you have to get together, you have to become involved. When you become involved, I know there are parents that do bake sale because this is what they can, but they understand that you cannot wait. And they have shown that getting together, making this community smarter and better, and more resourceful, they are able to change the face of this disorder. That's why I really want to thank you for all coming here, because this means that you all care, and when you put it together, all together, you can change the face of this disease that for 100 years we thought is not possible to fix it. But at least right now, there are several clinical trials, and hopefully there will be more, that these clinical trials will show that it is possible to improve cognitive function in people with Down syndrome. Thank you very much. Any questions? Sure. Oh, let me.
Benim bir iki sorum olacak. Öncelikle bu ilacın yan etkilerine ilişkin...
I'm sorry, it looks like your microphone doesn't work, he says.
Çalışıyor.
Yeah, this is working.
Bu ilacın yan etkilerine ilişkin de belirli bir tespitiniz var mı yaptığınız araştırmalarda? İkinci sorum, ilaç belirli bir süre kullanıldıktan sonra sonuç veren bir tedavi şekli mi? Yoksa bu ilaç ömür boyu kullanılmayı mı gerektiriyor? Ve insanlara ne zaman, yani ilaç ne zaman insanlar için kullanıma geçebilecek aşamaya gelir? Teşekkür ederim.
There is no drug with no side effects. If anybody tells you that there is a drug with no side effect, is lying to you, meaning that every drug will have some side effects. But the problem is that we want to reduce the side effects. We want to minimize them, to have the least amount of side effects that the drug will cause. Now, in order to take our drug to a clinical trial in the United States costs $1 billion. That's why it needs an enormous amount of resources to be able to take this drug to a clinical trial. Now, the strategy that we use to speed this up is that use similar drugs that are already approved in the US, and then see whether those drugs would do the same thing. And if that works, then we speed up the process enormously, because we don't have to go through all those regulatory aspects. Now, your question is that, do we have to give this drug all the time? Not necessarily, Because what we are learning is that when you give this drug for a few weeks, at least in mouse, it's also starting changing the structure of the brain, making more of these connections. When you make more of these connections, apparently when you stop, it would not go backward. Sure. Oh, go ahead. Yes.
Özür dilerim. Benim bir sorum daha vardı ama yanıtsız kaldı. Ne zaman acaba insanların kullanabileceği aşamaya gelebilir? Kaç yıl alabilir böyle bir süre?
As I mentioned, the drug right now is in phase 3 clinical trial for a different disorder. It's for hypotension, but it is right now tested in humans. But as I mentioned, for Down syndrome, what we are doing is that we are trying to focus on the similar drugs that are already being approved. And once we identify that, we don't have to go through this process, because what we identified is not a matter of one drug. It's a matter of this process. Once we have the process is wrong, then any drug that fixes this problem would fix, cognitive dysfunction, cognitive function in people with Down syndrome. That's why I'm really hopeful that very soon we would be able to find these drugs that being used for many, many years in humans and have shown that don't cause side effects, and see whether those drugs would be able to increase cognitive dysfunction. But you got to be careful is that even if a drug works perfectly in mouse, does not necessarily mean that it's going to work in human. Everything has to go step by step and test it. Once we go through these processes, then we identify, yes, the right drug, yes, is able to do the job, yes, is not causing cognitive dysfunction, yes, it does what it's supposed to do in humans. But that's the stage that we have to go through. And again, the more resources, the faster we'll go.
If you're finished, I'm English.
Oh, okay.
I'm not.
I think I need a translator to go ahead.
Okay. I'm not deeply into research area. I am from clinical side of Down syndrome, so I'm speech clinician. As much as I understand, there is a trial, MILES trial. You working on a clinical trial with mice on what is it called? Nafamine, something.
The
drug,
or drug,
yeah.
LDOPS.
LDOPS, right, okay. How long do you think this drug will be used in Down syndrome population approximately? Because what you said about all MILES trials. So people here, parents, educators, blah, blah, and few doctors. People might think that, oh, we've got drug now, so let's use it. So can you highlight the limitations?
I mean, the dose of the drug that we use in mice was significantly high. That's why first of all, what we have to do, we have to bring down the dose. We have to fix the dose. Okay, that dose certainly would not be acceptable to use it in clinical trial. That's why the first thing is to bring it down. Once we bring it down, as I said, I think we have a better strategy, because let's put two strategies here. I have a drug in my hand, it's not approved by the FDA, and it may take billions of dollars to take it to clinic. On the other hand, I could find drugs that are already approved by the FDA and could do that. That's why I think the other strategy, hopefully next time when I invite me, I'll talk about those. When those drugs would work, they significantly speed up this process of translation.
But you are not naming those drugs.
Certainly not.
No.
Certainly not.
Okay, so this is promising trial, so we don't have any cue yet.
Not yet.
We use an educational strategies which, you know, reinforce
Absolutely.
cognitive functions, blah, blah. So we're still on trial. We're trying it. Yeah,
Absolutely.
okay.
I mean, customized learning, customized classes,
Okay.
improving physical activity, you know, improving, let's say, music therapy. All these, as you know better than me, all these have shown that they are somehow effective in, you know, some aspects of Down syndrome. But none of them have been able to drastically change the course of the disease. I think there is no magic bullet here. There is no single drug that can fix it, and there is no single speech therapy or physical therapy. They all have to go together.
Yeah, that's what we're doing for a very long time. So any B, vitamin B, or that sort of vitamins you can think will be beneficial? Vitamin
Not
12?
No, not that I know. I don't have a share in any company with, with vitamin B.
Yeah, just the
But
knowledge.
no, I
Okay.
don't think so. I don't think there are a lot of people that thinking that, oh, these vitamins or different types of drugs may work. One thing that we have to be careful, because most of targets are children. And because most of these drugs are able to fundamentally change the structure of the brain, that's why we have to be absolutely sure to use them and then use them.
Yeah, also another aspect, I mean, when you use drug, people with Down syndrome cannot understand the side effect, you know, because they've got limited insight. So how those children will say, oh, I have a headache, or I've got bad stomach, blah, blah. So it's gray area, isn't it?
Oh, absolutely, absolutely. But there are right now, there are specific measures that have been developed to quantify cognition in people with Down syndrome. And then what we are trying to do is that we will eventually use those cognitive measures that are acceptable to everyone, and those clinical measures would determine whether if I use drug A, would it improve it or no. That's the idea. That's the idea. But right now, as I said, we have this drug. It's not approved, but hope is that we get different types of drugs that would do the same job.
Okay, very promising. I am very impressed.
Oh,
so
thank you very much. Thank you so much.
Thank you. Another question, Arthur?
Sure.
Öncelikle hoş geldiniz. Benim sorum güncel Alzheimer tedavisinde kullanılan ilaçlardan, örneğin donazepil gibi ya da nöropsikiyatrik ilaçlardan herhangi birinin beyin omurilik sıvısı içerisinde norepinefrin düzeyini artırıcı bir etkisi var mıdır? Bugün bir Down hastası görseniz, Down sendromlu bir hasta görseniz, bir bebek görseniz ne tedavi başlarsınız? Bir üçüncüsü de Down sendromunda tedavi başlamak için bir yaş kriteri düşünüyor musunuz? Yaş kriteri var mıdır? Teşekkür ederim.
Yeah, thank you very much, first of all. Right now, I mean, a few months ago, there was a paper from a different group that showed if you use a drug that is used in ADHD, and that drug is able to significantly increase the level of norepinephrine, they used that drug in mouse models of Alzheimer's disease. And that drug significantly improved the memory, meaning that there is hope that when you use this drug, it also works in Alzheimer's disease in two ways. First, improving cognition. Two, reducing pathology. Now the question is, when should we start? We have found that our drug works after locus coeruleus is significantly degenerated. Even after that, was able to function, meaning that even after the age that we know, oh, locus coeruleus is completely degenerated, it doesn't make norepinephrine, still our drug was able to function. The sooner, the better, but that doesn't mean that if you use it in adults, which in our mice, like let's say 3 months, it still doesn't work. It worked. Yes? Right.
It's a cycle that they say is very helpful individually.
In people with Alzheimer's and Down syndrome? Oh, I don't know. I don't know about the role of interleukins. I know our mouse model shows a sign of inflammation, and some of the drugs are able to reduce inflammation. But I'm not aware of the role of interleukins.
Dr. Griffin has an article
Right.
in New England Medical Journal,
Right.
February 21
Right.
and 2013.
Right.
And his article, he says this, he discussed about these interleukins that significantly change in the brain function and depress the Down syndromes.
Depressed Down syndrome.
Yeah,
But on the cognition or depression?
we have the article here.
Right. I think it's because these are different networks have different functions. That's why you may be able to improve mood, but that doesn't necessarily mean that you can improve learning and memory.
Neuroglia cells, it says in the neuroglia in the brain,
Right.
it change the expression of the interleukins
Yes.
in action of the neuroglia cell in the brain.
Okay. Let me tell you a story. The story is for each neuron in the brain, as you know very well, there are 10 microglia, 10 glia cells, right? These are supporting cells. They support the function of cells. What do? They clean up the mess, meaning that they clean all these amyloid that is formed in people with Alzheimer's disease. When you use our drug, it has been shown that these microglia move toward the plaque, clean it up, and destroy that. Meaning that that's the mechanism. The mechanism that norepinephrine reduces pathology is exactly what you're talking about, is by acting on microglia.
Thank you very much for your
No problem.
speech. I have a couple of questions. First is, I think you were talking about atomoxetine, the ADHD medication which increases norepinephrine. Do you think it's preferable now to use it instead of the stimulants for kids with ADHD, so that we shoot two birds with one stone, ADHD and the development of Alzheimer's? And secondly, do you think it has to do with synaptic pruning, the age of use, so that if we think that locus coeruleus pruning probably goes on until like
Right.
20s or so, like late teen
Right.
years, do you think it's worthwhile to keep on this norepinephrine enhancers until that age?
I mean, unfortunately, when they used atomoxetine by itself was not able to fix the problem. They had to mix it with our drug. That's why, because the level that atomoxetine is able to increase norepinephrine, it wasn't that much. That's why either you have to give a huge dose, which is obviously is very dangerous, or it's not enough. That's why atomoxetine could be one potential factor, but looks like it by itself is not able to significantly improve cognition in our mouse model. And then the question is, what's the age? I know this is a very critical, That's why one fundamental aspect that has not really been studied in Down syndrome is that if we see these changes in people with Down syndrome and in our mice, Is it developmental? Did it happen first? Or no, it was fine, but it's degenerative. It happened because they age longer, because they live longer. We have not been able to break this down. Because of that, I don't know whether most of these changes are developmental and it's a matter of pruning, or no, it's not a matter of pruning. There is some extra factor there and killing these cells and causing this cognitive dysfunction. Yes?
Sayın Selay,
I'm sorry. I'm sorry, I could not understand. Right. Not on the epinephrine, but obviously Down syndrome is not just a matter of norepinephrine. But I don't think has been tested. Has not been tested in our mice. But if you're asking me to guess, probably will work. But as you know, for non-steroidal anti-inflammatory drugs, it has to be used on the right time. Because if you don't use it on the right time, it's actually accelerate the process. Right.
evet.
Please go.
Sayın Selay,
Aha.
Amerika'da kullanılmakta olan Nutrivin D beslenme destek programından haberdar mısınız? Bu program içinde kullanılan destek, ilaç demiyorlar tabii, beslenme desteği olarak anlatılıyor. Alzheimer hastalığına etki ettiği söyleniyor idi. Bu da sizin bu bilişsel düzeyi etkilediğini biliyor musunuz ya da bizi yönlendirebilir misiniz?
There are a lot of companies making money, but making supplements for Alzheimer's disease, and majority of them don't work. That's why I don't know about this particular drug, but most supplements have entirely failed in terms of improving cognition in people with Alzheimer's disease. And the reason that they use it as a supplement and not drug is a regulatory decision, because it would be easier to bypass the regulations. But I'm not aware. You see, you have to see whether fundamentally and independently people who are not involved in those studies can really show that. And yet to anybody really show that these supplements can indeed improve cognition, they have no hands into making those drugs, they have no profit in making on drugs, and they're entirely independent.
Öncelikle merhaba, buradayım.
Okay.
Merhaba. Siz demiştiniz ki çalışmanızda 3 aylık farelerde çalışmıştınız. Bir de ne kadar erken o kadar iyi dediniz. Yalnız biz biliyoruz ki Down sendromlu çocuklar anne karnında tanısı konuyor. Down sendrom olarak dünyaya geleceği. Peki bu neroprinin kullanımında anne o ilacı hamilelik süresince kullanırsa ne olur? Hani ne kadar erken o kadar iyi demiştiniz ya.
Right now, I'm not advocating use of any drugs in pregnant women, because first, for anything that you would use, it has to be absolutely make sure that it's safe. That's why I don't think it's a good idea to show norepinephrine or any similar drug using during that period, that very precise and very important time of pregnancy, to use that before we 100% make sure that this drug does not cause significant side effects. That's why it is really tricky. That's why you've got to be really, really careful.